Hello everyone from Math 2000, Linear Algebra. Professor Wenson here again with a video on your Zybooks section 7.2 titled General Linear Transformations. So you saw in section 7.1 what a linear transformation between Euclidean spaces looked like and what properties they satisfied, right? There was that additivity property and homogeneity property. Those two properties are still the same here, but instead of looking at transformations from a Euclidean space to another Euclidean space, like from say R2 to R3 or R4 to R7 or something, we're going to be looking at transformations from a general vector space called U to another general vector space called V, and we'll call V. And these vector spaces could be that those spaces of polynomials of degree n or less, those p sub n spaces, the set of all m by n matrices with real entries. Could be that vector space. Could be the space of continuous functions over some interval. Now we're just looking at general transformations between vector spaces. All right. So again, the definition and properties of Euclidean vector spaces can be generalized to include sets such as that p sub n, which was this was all polynomials of degree n or less, and maybe R 2 by 2. This is that set of all 2 by 2 polynomials. So for instance, the mapping T from Pn to Pn minus 1 defined by T of some polynomial of degree n or less equals its derivative, right? This would be a polynomial of degree n minus 1 or less, is also a linear transformation. Right? It would satisfy that additivity property and homogeneity property, and we're going to see stuff like that later. Also, a method exists for finding the standard matrix of a linear transformation that applies to general vector spaces and not just Euclidean vector spaces. When we talk about the standard matrix of a linear transformation, between non-Euclidean vector spaces, the columns of that standard matrix are going to end up being coordinate vectors relative to some basis. Again, we'll see all this later. All right, so the first part is just evaluating general linear transformations, just taking a transformation and evaluating it, plugging in some input, getting some output. All right, so a linear transformation T from vector space U to vector space V can be defined between any two arbitrary vector spaces U and V. The terminologies introduced in the previous section still apply, right? So like that, U is the domain, V is the codomain. You have images, pre-images, all that stuff. Range. The range was the set of all actual outputs and all the same terminology. All right. So I'll write out a couple of these. Actually, you know what? I'll read through these and go and do the activities. Right. So A, you see this transformation T1 takes an input from R2, right? So a vector with two components, and then its output is from P1, which are those polynomials of degree 1 or less. And here's how it does it. It takes a vector x1, x2 and outputs 5 times x2 for the constant term, and then minus 3 times x1 times x for the linear term of the polynomial of degree 1 or less. So if I'm putting in the vector 2, 0, we'd have 5 times 0, so 0 for the constant term, and then negative 3 times 2 times x, so negative 6x for the linear term, and you see the output is the polynomial negative 6x, as you're seeing in the solution here in part A. For the second example, T2 is this transformation from the set of 2 by 2 matrices, right, with real entries R2 by 2, to the set of vectors with 3 components, R3. And it does it this way. It takes a 2 by 2 matrix with entries A, B, C, D, and its output is a vector with 3 components. The first component is -4 times A, second component is B plus 2, third component is C plus D. So they say, what would be the output if the input was this 2 by 2 matrix? So the first component would be -4 times -1, or +4. Then B plus 2, so 3 plus 2, 5 for the second component. And then C plus D, -2 plus 0, which would be -2 for the third component. So 4, 5, -2, and you're seeing that here again in part B in the solutions. In this final example up here, transformation T3 goes from the set of all polynomials of degree 3 or less to the set of polynomials of degree 2 or less, and the transformation is just the first derivative. Right. So T3 of some polynomial P of x of degree 3 or less is mapped to the derivative of that polynomial, which would be a polynomial of degree 2 or less. And if I plugged in x cubed minus 5x squared plus 6, the output would be the derivative of this, which would be 3x squared minus 10x. You're seeing that down here. So pretty simple examples, I think, to start. Again, you're just plugging in values and evaluating. All right, so I'll write out some of these and on a piece of paper, and we'll take a look at some other examples. All right, so here's the transformation given to us in the first example in that activity. We have, it's called T1, and your input is a polynomial of degree 2 or less. Your output is going to be some vector with 2 components, and they describe how that works up here. Now if I plug in a specific input, the polynomial they're giving us is, plug in 2x squared plus 5x minus 9. So this polynomial, if it's set up this way, the value of a1 is 2, the value of a2 is 5, the value of a3 is -9. So the resulting output, the first component is a1 plus a2, so 2 plus 5. And the value of the second component is a1 plus a3, so 2 plus -9. So this output has components 7 and -7. Right, so 2x squared plus 5x minus 9, this vector from P2 would map to this vector 7, -7 from R2. Right. Let's go back and look, and they say, hey, would this map to 7, 7? No, I said it would map to 7, -7, not 7, 7. All right, let's look at one more of these on paper. Okay, so we're given this transformation here. It takes your input as a vector with from R3, so a vector with 3 components, and your output is a matrix, 2 by 3 matrix. And they describe how that's done here. Right. And then we were asked to find, what's the value of T2, when the input is the vector with 3 components, the vector with components 1, 0, 3. Alright, so this 1 is the x1, 0 is the x2, 3 is the x3, and just make those replacements on the other side and we get our output. So 1, 2, I'm sorry, 1, 0, 1, 0, 3 be our first row, x1, x2, x3, and then double all those for the second row, 2, 0, 6. And there's the output. This vector 103 maps to this matrix with the first row 103 and the second row 206. And that's it. And they're saying, hey, it would map to this. No, it wouldn't. The second row would be 206, not 103. All right, and you can look at the last one and try that on your own. All right, then for the challenge activities, I'll just kind of do one of these out loud. These aren't the toughest things, I don't think. So you see here I'm going from P2 to R2, the polynomials of degree 2 or less, so my input you see is a quadratic polynomial. My output is a vector with two components. And just pay attention to what's A1, what's A2, what's A3. So in this input here, the input is 4x squared plus 6x plus 3. So 4 is the A1, 6 is the A2, 3 is the A3. The output, the first component, is 2 times A1, so 2 times 4, minus 2 times A2. So 2 times 4 minus 2 times 6, 8 minus 12. So the first component's negative 4. The second component of the output, 3 times A2, so 3 times 6, 18, plus 6 times A3, 6 times 3 is 18, 18 plus 18, 36 for the second component of the output. And then I believe all levels are like this, where you have an input from some vector space, so here the input is from R2, the output is a 2 by 2 matrix, right, from R2 by 2. And for the third level, it's that derivative transformation again. So again, should be relatively simple to evaluate. All right. Now the next part of this section is similar to what you did in section 7.1, where you're determining whether or not a transformation is linear. Right? Is a transformation a linear transformation? So it'll still, it still has the same definition. A transformation is linear if and only if it satisfies these two properties. So if for every pair of vectors u and v from the domain, t of u plus v equals t of u plus t of v. And if for every vector v from the domain and every scalar r from some field, usually it's the real numbers, t of rv is equivalent to r times t of v. So you could say that, additivity is preserved, scalar multiplication is preserved through the transformation. So let's look at an example. All right. So I'll write this on paper, and then again we're asked to determine if this transformation satisfies these two properties. Is it linear? So this might involve a little more writing than you'd like, but still take your time and get through it, and you'll see if it's linear or not. Okay, so we're given this transformation. It's from the set of 2 by 2 matrices with real entries to the set of the vector space of polynomials of degree 3 or less. And it simply takes the entries of the 2 by 2 matrix and makes them the coefficients of the polynomial. That's the transformation. And the question is this transformation a linear transformation? So again, we have, just like the section 7.1, we have to answer those two questions. Does it satisfy those two properties? So does the additivity property hold? So in order to do these, I'm going to have my vector u. Right, these are coming from the domain, and the domain is 2 by 2 matrices, so this is going to look a little weird maybe, but vector u is a 2 by 2 matrix with, say, components u1, u2, u3, and u4, like that. And vector v, also coming from the domain, is another 2 by 2 matrix with components, say, v1, v2, v3, and v4. And, suppose r comes from the real numbers, right? This is a scalar. All right, so I'm going to let all that stuff happen. And then the question is, is t of u plus v equal to t of u plus t of v? Just like I did in the previous section, I'm going to look at both sides separately and see if we get the same thing back. All right. So let's take a look at the left side. So you have t of u plus v. So this is one where you add the vectors first and then apply the transformation. Now, I didn't say anything about any change to the way vectors are added here. Here the vectors are matrices from the domain. And so I'm going to assume the usual vector matrix addition and scalar multiplication here, because they didn't say otherwise. So this is t applied to, and then when I add u and v together, the usual way, you'd have u1 plus v1 for the first component, first row, first column, u2 plus v2 for the first row, second column, u3 plus v3 for the first row, second row, first column, and u4 plus v4 for the second row, second column. All right, and then I'm going to apply the transformation to this. Okay, and in that transformation, just in this order, right, those become the coefficients of my output polynomial. So the output is u1 plus v1 times x cubed plus u2 plus v2 times x squared plus u3 plus v3 times x. Finally, the constant term is u4 plus v4. All right. And if you'd like, you can distribute a bunch. This is the same as u1 x cubed plus v1 x cubed plus u2 x cubed x squared plus v2 x squared plus u3x plus v3x, and then plus u4 plus v4. Okay, so there's the left side. Now you could probably show me that's equal to the right side right here, but now I'll start with the right side separately. Now the right side of this statement is I'm looking at t of u plus t of v. Alright, so for t of u, I'm applying the transformation here to vector u. So t of u would give me u1 x cubed plus u2 x squared plus u3x plus u4. There's t of u. Plus, and then t of v, I apply the transformation of vector v here, matrix v. It'd be v1x cubed plus v2x squared plus v3x plus v4. And can you see that these are the same? These two expressions are exactly the same. Right, you got your u1x cubed term, v1x cubed, and so on. Okay, you can see that they're the same expression. So, for any pair of vectors in the domain, for any pair of matrices, t of the sum, when you apply t to the sum of those matrices, you get the same result as if you were to apply t to the matrices separately and then add them. Alright, so yes on additivity. Check on that. Alright. Alright, and then the next part of this is, does the additivity hold yes. The second part is, does that homogeneity property hold? So, for I'll take, vector u or v, whatever. Is the following true? Is t applied to r times v equal to r times t of v for any vector v from the domain, for any matrix, any 2 by 2 matrix, and any scalar r? So again, I'll do the left side and the right side separately and see if they're the same expression. Give me the same result. Now t of r times v would be t of, this is where you do the scalar multiplication first and then apply the transformation. Now if I do r times v, that'd give me rv1, rv2, rv3, and rv4. Right, and then if I apply the transformation, this is going to be rv1 times x cubed plus rv2 times x squared plus rv3 times x plus rv4. Okay. Now let's look at the right side. And look at the right side. What is r times t of v? So this would be r times, and then t applied to vector v, or matrix v. So that'd be v1x cubed plus v2x squared plus v3x plus v4. And can you see that when I distribute the r here, these expressions are the same. The left side and right side are the same value, the same expression. Right. So we do have homogeneity. T of r times vector v is equivalent to r times t of v for any vector v from the domain and any scalar r. And since both these properties hold, since the additivity and homogeneity properties both hold, both are true, we would say that T is a linear transformation, between these two vector spaces R2 by 2 and P3. But I'll just write T as a linear transformation. Okay. And they go through that here in the example, when they show the solution here. They use different letters than I do, but it's the same setup. Alright. Yeah, so again, it's just like in the section 7.1, it's pretty easy to determine by looking at these whether or not they're going to be linear. Basically, if all the parts, if like all the coefficients or all the entries of a matrix or all the entries, components of a vector, if they're just linear combinations of the components of the input, then it'll be a linear transformation. So like here, this is from P2 to R3. See, my polynomial of degree 2 or less is plugged in, and the output is a 3-component vector. See, this first component is 1 times a1, 0 plus 0 times a2 plus 0 times a3, but then you got this plus 1 here. That throws everything off. So this first component is not a linear combination of the input components. So this is not going to be a linear transformation. All right, and I'll give you an example as to why the additivity property wouldn't hold. Okay, so here's that rule, that transformation we're given. And again, I'll show you an example as to why the additivity doesn't hold. All right, so let's say vector u from the domain is I'll just say it's x squared, just 1x squared. And let's say another vector from the domain say vector v equals. Now let's go 2x squared. Why not? Just real simple ones. All right. Now, let's look at t of u plus v. Now t of u plus v, this is adding the polynomials first, right? Adding the vectors first. This would be t of 3x squared. And when I apply the rule, we get an output. We'd have 3 plus 1 as the first component, so 4. And then 0 plus 0 and 0, so 0 and 0 as our second and third components. Now let's look at the other way around. What's t of u plus t of v? Well, if I apply t to this x squared, my first component is going to be 1 plus 1 or 2, and then the other ones are going to be 0. Right, I picked some easy ones. And when I apply t to v, when I apply this transformation to 2x squared, the first component of the output is going to be 2 plus 1, which is 3, and then the other components are zeros. And then adding these together, usual vector addition here, it's 5, 0, 0. What you are seeing is not equal to the t of u plus v. So there's a counterexample to the additivity property. And you can think of your own and stuff, but again, it's very easy to tell. If you notice that all the parts of your output here, this is not a linear combination of A1, A2, and A3. Not a linear combo of A1, A2, A3. And it's because of this plus 1 that's added on there. That throws everything off. So we can see that additivity doesn't hold. Right, so this transformation is not a linear transformation. So does t preserve additivity? No, I just showed you an example as to why it doesn't. Now again, they go through the whole thing of showing you the left side with some general vectors, the right side with some general vectors, and saying, hey, these first components are off by 1. So they're not always going to be the same. Does it preserve the homogeneity property? So if I took a vector here, get this, multiply this by r, then you'd have RA1 plus 1, RA2 plus RA3, RA3. But then if I took r times this whole thing, it would be RA1 plus r. So the first components wouldn't be the same all the time again anyway. Again, this plus 1 here throws everything off. Now you can go through again and do the general rules and show that the left side is not equal to the right side in general for that homogeneity property, or just give an example. Right. And then, t is a linear transformation? No way. I mean, it doesn't satisfy the homogeneity property, doesn't satisfy the additivity property. And you can do s. Right. Now, you could also write this output here. You know what the derivative of a quadratic polynomial is. This would be 2a1 times x plus a2. You could just write that as well as the output and see if it's linear. And I'll tell you right now it is. You can figure it out though on your own as well. All right. In the last part of this section, you saw this in section 7.1 as well. It was a little easier in that section when the domain and the codomain were both Euclidean vector spaces, R2 and R3 and stuff. But we're going to be finding the standard matrix of a linear transformation. And this is for really any linear transformation as well. All right? But it's got to be linear. All right? Only linear transformations have a standard matrix that represents it. Okay. So I'll read through this. Hopefully it makes some kind of sense, and hopefully it makes more sense when I actually go through an example or two. So the standard matrix of a general linear transformation is uniquely determined by the images of each standard basis vector of the domain U under the transformation. The images of each basis vector of U under T form the columns of the standard matrix of T. Well, they should say the coordinates of the images relative to a basis for V, but no, we'll see all that in a second. So here, suppose T is a transformation, a linear transformation from vector space U to vector space V. And suppose this fancy B thing here, this set of vectors, is the standard basis for the domain U, and B prime, which composes of a bunch of other vectors, is the standard basis for the codomain V. Then a matrix A exists such that, now hopefully you remember your coordinate vectors from a previous chapter. The coordinates of T of x relative to B prime will be equal to this standard matrix times the coordinate vector of x relative to B. Right, again, where the columns of A are formed by the weights of the image of each basis vector of U. Alright, so let's get into what all that means, alright, with an example. So I'll look through this activity example. Okay, so here's a transformation that we actually saw earlier. And it's that transformation from the vector space of 2 by 2 matrices to the vector space of polynomials of degree 3 or less, where each of the entries of the matrix in this order are the coefficients of the polynomial. Right. So what I'm going to do is I'm going to put up this B and B prime that they talk about in that theorem earlier. B, this fancy B, and this is going to be the standard basis of the domain for R 2 by 2. And you've seen this, right? You've seen the standard basis for a set of m by n matrices. And the standard basis for R 2 by 2 would be 2 by 2 matrices where there's 1 in one position and 0 everywhere else. So this vector, this vector, right? This, and one more. Here's the standard basis, and they would call this, so this vector is like the E1 that you saw. This vector is the E2. This is the E3 and E4, right? And it's R2 by 2. Remember, the dimension of this should be 4. You see there are 4 vectors here in the standard basis for R2 by 2. And then the B prime that they talk about in that theorem. All right, this will be the standard basis for the codomain, which is the P3. Now, you got to pay attention to order, the order you put things in. I'm actually going to put this in a different order than they do in the activity. Right. So a standard basis for polynomials of degree 3 or less are linear combinations of x cubed, x squared, x to the first, and 1. Right. Every polynomial can be written as a linear combination of these 4 vectors here, and these are also independent vectors. And these vectors would be in the theorem. This x cubed would be my f1. This x squared would be the vector f2. This would be f3. And this would be f4. Right. So again, the P3 has a dimension of 4. Now, what this theorem states, right? When they're talking about the standard matrix for a linear transformation, we're going to find the image or the output for each vector in the standard basis of the domain. Alright, so I'm going to start off doing that, and then when I get my output, my image, I'm going to translate it to its coordinate vector relative to basis B prime. Alright. So what's t of E1? Alright, so again, I just called this E1 because I didn't want to write it again. So t of E1, 1, 0, 0, 0, would be just 1x cubed, right, plus 0x squared plus 0x plus 0. And then what I'm doing over here is I'm going to write out the coordinates. I'm going to write the coordinate vector relative to basis B prime, relative to this ordered basis that I put here. You see this is 1x cubed, 0x squared, 0x, and 0 times 1. So 1, 0, 0, 0 are the coordinates of this output relative to B prime. Again, hopefully you remember the talk about coordinate vectors. That would help here. Maybe go back and take a look at that again. Alright, what's the image of E2? Right, the second standard basis vector, this matrix, with the 0, 1, 0, 0. Well, this would be 0x cubed plus 1x squared plus 0x plus 0. And again, I'm going to translate this to its coordinates relative to B prime. So again, the way I wrote B prime is this order. So you see it's 0x cubed, 1x squared, 0x, 0 times 1. And this is again the coordinates relative to B prime. And what's t of E3? Right, the image of the third standard basis vector. The third one here is 0, 0, 1, 0. I plug that in to this transformation. I'm going to get 0x cubed plus 0x squared plus 1x plus 0. And again, I'm going to translate this to its coordinates relative to my B prime here. And this is 0x cubed, 0x squared, 1x, and 0 times 1. And there are the coordinates relative to B prime. And then finally, right, what's the image of E4, right? The fourth standard basis vector, this polynomial. It'd be 0x cubed plus 0x squared plus 0x plus 1. Right? 0x cubed plus 0x squared plus 0x plus 1. And then if I write the coordinates of this relative to my ordered basis for the codomain, that B prime, the coordinates are 0x cubed, 0x squared, 0x to the first, and 1, like that. All right. And then each of these form the columns of the standard matrix for this transformation. All right. So these are the columns. These coordinate vectors are the columns of the standard matrix for this transformation. Right. So that standard matrix, which they're calling A. Right, so the standard matrix for T called A is going to be basically a matrix where those are all the columns. 1 0 1 0 0 0 0 1 0 0 0 0 0. Oh, sorry, 0 0 1 0. The third column, and 0, and then 0 0 0 1. That's a 1. Sorry. It's a 4 by 4 matrix. And then how this is going to relate back to the original is the following. Remember they said this? They said that the coordinate vector of t of x relative to b prime, right, is going to be equal to A, the standard matrix, multiplied by the coordinates of the input relative to B. Right. So let's think of how that would, let's see how that would look. So basically what that's saying is this. If I take, again, this, let's call this general matrix here, back in the original rule, call that vector x. So then this, over here, this polynomial would be t of x. And if I write the coordinates of that, if I write the coordinates of this relative to b prime, right, now remember b prime was this set here with x cubed, x squared, x, and 1. If I write the coordinates of this relative to b prime, we're getting the following. There's a11 times x cubed, then a12 times x squared, a21 times x, a22 times x times 1. Right. And so this is relative to b prime here. This is equal to my matrix A, right, this 4 by 4 matrix. 1, I'll write it again. Times, and then the coordinate vector of x, right, this is my vector x here, but the coordinates relative to the standard basis b. So you have a11 times this first, a12 times this second, a21 times this third, a22 times this fourth. And that's what I'm getting here. A11, A12, A13, sorry, A21, A22. And this is relative to B. So, I mean, this should be pretty obvious, though, because, what is this matrix here? This is the identity matrix I have. So they're saying our coordinates, the coordinates of the input vector relative to B are the same as the coordinates of the output polynomial relative to b prime. Right. Which is pretty obvious here, right? Which should make sense. Let's try this out with some actual values. Right. So let's say, for instance, I wanted to find t of, and then this matrix, say 1, 2, 3, 4. So again, this would be my vector x, right? Well, if I run it through this rule here, we're going to have the coordinates of this relative to b prime, right, that x cubed, x squared, x, and 1 set, the standard basis for a P3, will be equal to A, which is just the identity matrix. See, this is just the 4 by 4 identity matrix, times the coordinate vector of my input relative to B. Right. And A is just the identity matrix I4, and this coordinate vector of 1, 2, 3, 4 relative to the standard basis B is just the vector 1, 2, 3, 4 going up and down like this. And so we get 1, 2, 3, 4. And this is telling me that 1, 2, 3, 4 like this are the coordinates of my output relative to basis B prime. Meaning that my output, T of 1, 2, 3, 4, is 1x cubed plus 2x squared plus 3x to the first plus 4. All right. Which you could have easily done. I mean, I know you could have done this without doing coordinates, but there's a reason we're going into translating things into coordinates, trust me. Okay, so let's look at a different example. All right. That one was kind of too straightforward. See, they did it the other way around. They had 1x squared and x cubed for b prime instead of the way I had it. See, it changes the order of things. So let's look at a different example. All right. So in the next example, they're giving us this the derivative transformation again, and it is a linear transformation. Okay, only linear transformations have a standard matrix. So we're going, our input is polynomials of degree 2 or less. Our output would then be a derivative of that, which would be a polynomial of degree 1 or less. All right, and they're saying, find the standard matrix for this transformation. All right, so in order to do that, I need a standard basis for each of the domain and codomain. So again, I'll have B here be this, the standard basis for P2. Now this time I'll do it in the other order where I start with the constant first. It really doesn't matter. So remember, every polynomial of degree 2 or less is some linear combination of 1, x, and x squared. Right? So there's the standard basis for P2, the domain. And I'll put up the B prime. All right, this is the standard basis for P1. Now every polynomial of degree 1 or less can be written as a linear combination of 1 and x. Right. So, this is the standard basis for the codomain, right, for that P1. Now to find the standard matrix, I just need to find the image of all the standard basis vectors from the domain and then convert them to their coordinates relative to the standard basis B prime for the codomain. So what's T of 1? All right, so again, I'll call these, these are the E1, E2, and E3, and these are the vectors F1 and F2 from the theorem. So what's T of E1? What's T of 1? Now T of 1 would simply be 0, right? The derivative of 1. And then what I'm going to do is I'm going to translate this to its coordinates relative to B prime. So 0 is really just 0 plus 0x, right? So 0 times 1 plus 0 times x, so the coordinates in the proper order are 0 and 0. So this would be the coordinate vector, again, relative to B prime for this output. And this is going to be the first column of my standard matrix for this transformation. Alright, then what's t of x? Well, the derivative of x would simply be 1, which if I write it in terms of the vectors of b prime, that's 1 times 1 plus 0 times x. So when I translate it to its coordinates relative to b prime, those coordinates are 1 and 0. Right? 1 times 1, 0 times x. And this will be the second column of my standard matrix. And then finally, what's t of x squared, right, the E3? Well, that would be 2x, which if I write it, in the order that I have in b prime, that's 0 times 1 plus 2 times x. So the coordinates, right, when I translate this to its coordinates relative to b prime, it's 0 times 1 plus 2 times x. Okay. So these are the columns of my standard matrix. All right, so the standard matrix for this transformation, which I'll call A, is going to be a 2 by 3, where the first column is, again, these coordinates, 0, 0. Second column, 1, 0. Third column, 0, 2. All right, and then putting this all together, with what it says in that theorem, we have the following. So, the coordinates of any output, say t of p of x, if I take a polynomial, plug it into t, and write the output coordinates in terms of if I say what are the coordinates of the output relative to b prime, right, the standard basis for the codomain, the outputs, this should be equal to a times the coordinates of the input, the coordinates of the polynomial, relative to the standard basis for the domain. Right. So, for example, all right, they're asking us to use this standard matrix. They're asking us to use this to help find t of 3x squared minus 5x plus 7. All right, so we're going to use this to find the following. What's t of 3x squared minus 5x plus 7? Now I know you can easily find it. We know that this is going to be 6x minus 5, right? The output's the derivative. But let's put it in terms of this statement here involving all these coordinate vectors. So this is going to be an output, right? So this is going to be something in P1, right? The codomain. So if I want the coordinates of this relative to the standard basis, B prime, this 1 and x set, I can do the following. I can take matrix A, so the 0, 0, 1, 0, 0, 2, and multiply this matrix by the coordinates of 3x squared minus 5x minus 7, the coordinates of the input relative to the basis for the domain. Now, the basis for the domain I used was this. The basis was 1x and x squared. So this is, if I'm translating this to its coordinates relative to b, those would be the following. You have 7 times 1, negative 5 times x, 3 times x squared. These would be the coordinates. This would be the coordinate vector of the input polynomial relative to my basis b earlier. And then I multiply this by my standard matrix on the left here. This is a 2 by 3 times a 3 by 1, and I'd end up with a 2 by 1, wouldn't I? And let's see, the first row with the first column here, we get 0 plus negative 5 plus 0. So there's negative 5. And then the second row with the first column, you got 0 plus 2 times 3 is 6. And again, these are the coordinates of my output relative to B prime, negative 5 and 6. So remember, B prime was that set with 1 and x, those vectors 1 and x. So if these numbers are the coordinates of my output relative to B prime, that means my output, all right, t of 3x squared minus 5x plus 7, is negative 5 times 1 plus 6 times x. Which, I already told you it was going to be that, 6x minus 5 or negative 5 plus 6x. So that's how these coordinate vectors are going to be used, and these standard matrices. Now again, I know this wasn't, like, why are we doing this? The reason we're doing this is for later. You're going to see something called the fundamental theorem of matrix representation. Later, we're going to talk about things called eigenvalues and eigenvectors later. And they all kind of tie into writing an output as some sort of matrix times a particular input, where everything, the output, the input, the columns of the matrix, are all in coordinates relative to some basis. So right now it might not seem very important, and you can just like plug the thing in and get the output, but being able to write the coordinates of your output as some matrix times the coordinates of your input relative to certain bases is very important. All right? It may not seem that way now, but it will. All right? It will be important, much more important later. All right, so see all that here? Yeah. So, all right. So this one. And then you got a challenge. And that's it. But they're asking you to do the same stuff. So I'll kind of leave these to you. The video is like almost an hour long now. But you give another transformation, P2 to P3, defined this way. Every polynomial that you plug in, you just multiply by x, and you get a polynomial of 1 degree higher. See, this basis is the standard basis for the domain. This is the standard basis for the codomain. What's the image of the basis vector 1 under t? It'll just be x, right? You just multiply it by x. And then x squared when you plug in x. And then x cubed when you plug in x squared. And then what would be the standard matrix of t? Well, what are the coordinates of x under this basis for the outputs? That'd be 0 plus 1 times x plus 0x squared. So 0, 1, 0, 0 for the first column. So that's this one here. Right. And then see the second basis vector from B mapped to x squared, which relative to this would be 0, 0, 1, 0. So you see the second column is 0, 0, 1, 0. The third basis vector from the domain mapped to x cubed, which would be 0, 0, 0, 1 when you talk about coordinates relative to B prime, which is, see the third column, 0, 0, 0, 1. And then if they say, oh, let's use this, now again, it's just going to be x cubed plus 9x squared minus 3x. Very, very simple. But you could also take your standard matrix here and multiply it by the column, the coordinates negative 3, 9, 1. And you're going to see them do that here, and then get the output 0, negative 3, 9, 1. Right? And you see it's 0 times 1, negative 3 times x, 9 times x squared, 1 times x cubed. You get that x cubed plus 9x squared minus 3x as the output. So again, I know it's not super maybe intuitive yet, or why we're doing this isn't apparently obvious, because you can just plug the input in and get the output. But I'm going to tell you one more time, being able to write your inputs, your outputs, and these matrices, the columns of these matrices, being able to express things as coordinates relative to some basis is going to be very important. Alright, and you're asked to do the same stuff down here. Right, find the standard matrix of some transformations, maybe find some inputs, find some outputs. So I'll leave those challenge exercises to you. Okay. And then you have your additional exercises. Some of these are assigned, some are not. I would still recommend looking at all of them, right, just to get more practice, more exposure to the material, get better at it. And you have the solutions to look at too if you need to, fall back on that. But please, try to work on the problems, try to figure things out before you look at the solutions. Right? If you're just copying solutions down without trying, you're not going to learn anything. And hopefully watching this video is a decent guide. And I have some other videos that I've made as well on more individual objectives. So hopefully watching all my videos and other people's videos and reading the text and taking notes and doing all the stuff you should do as a student, hopefully all that stuff helps you out when you're going through this on your own. And let me know if you have any questions. Of course, send me a message. I'll get back to you as soon as I can. We get a lot of this done. Hope you have a wonderful time with it. And thank you very much for watching.